Hey folks, welcome to a short video about exponential and logarithmic models, mainly exponential models. This is section 4.6 in the book. So the good news is there's not really any new mathematics here from previous videos, just sort of applying the mathematics that we've developed to some real world scenarios or almost real world scenarios. So let's just start with a couple of exercises. These are from the notes and exercises, as you can see. And here's the one I want to start with, right? So you take some headache medicine, and once the medicine enters your body begins processing it. So the amount in your system decays over time. And we have the information that 200 milligrams decays after 4 hours to 120 milligrams. So the effects of the medicine wear off when the amount in your system dips below 80 milligrams. We want to know how long that takes, right? So how long does this take to happen? The 200 milligrams to decay to 80 milligrams. And we are going to assume that the amount of the medicine in your system decays exponentially, right? So this tells us what kind of model we're going to use. All right, so let's get started. First, I'm going to build the model, right? So for us, a model is always a function with an input and output, and it pays to identify those things as precisely as you can. So the input variable here is time, and I'm not going to just say let t equal time. That doesn't make any sense. I'm going to be clear about how I'm measuring it. It's the time since the first dose in hours, right? So the number of hours since you first took the 200 milligrams into your system. That's the input. The output will be the amount of medicine in your system in milligrams. So because that's the output, I'll write it in functional notation, M of T, M for medicine. Of course, you can name the variables whatever you want. Now we have here an exponential model, right? It's an exponential decay model. So right away, I know roughly what the function looks like. It's AB to the T was the sort of very first kind of exponential model we looked at. We could also use continuous growth form AE to the R minus T. And I know there'll be a minus sign in the exponent because it's a decay model. It actually doesn't matter a lot which way, which form of the model you use. It looks like I'm going to use the continuous model here. And we'll talk about, by the way, how to go back and forth between the two model types as well. Okay, so what I want to do in either case here, I have two unknown parameters. Here it's A and R, and here it's A and B. We know that A is the initial amount in either case. So usually, or I should say sometimes, I guess, we can go ahead and fill that in. Right here, we know the initial amount, that's the time zero amount, is the amount in your system as soon as you take the medicine. That's the 200 milligrams. So right away, I can half specify my model, right? Instead of A e to the minus RT, I can write 200 e to the minus RT. And now I'm going to use the other piece of information I'm given, namely that after 4 hours, the medicine has decayed to 120 milligrams. In terms of my model, that means M of 4 is 120, right? The amount of medicine after 4 hours is 120. And M of 4, here's M of T, right? So the input slots up there in the exponent. So when I put a 4 in for T, I get 200 e to the minus 4 times R equals 120. And I can now solve this equation. Right, so we've been solving equations like this in previous videos, so I'll go a little quickly here, a little more quickly, divide both sides by 120. And now to get to the variable, I want to undo the exponential base e, so I'll take a natural log of both sides. And when I do that, of course, the natural log of e to anything is the anything, so I just get the minus 4r on the right, and I get the natural log of 0.6 on the right, on the left rather, and the natural log of 0.6 on the right. A little better to use parentheses there. And then finally, I just divide both sides by -4. And when I do this thing on my calculator, it comes out to 0.1277. And so now I have fully specified the model, right? My model is 200 e to the minus 0.1277t because I figured out the value for R. Notice that if it's a decay model, there should be a negative sign here in the exponent. And if it's a growth model, then there should not be. So this is a decay model, so that looks about right. Now I think we can answer the question. The question is, when will the amount of medicine be equal to 80 milligrams? And actually, before we do that, a word about switching model types, right? So here is the model we just wrote down. And we did this once in a previous video, but I can take this exponential and rewrite it this way, right? Because when you raise a power to a power, as is highlighted in blue right now, you multiply the exponent. So I'll multiply the minus 0.1277 in the t and get right back to this again. And this thing inside the parentheses is just a number, that a numerical value I can get on a calculator. So if you do that on a calculator, e to the minus 0.1277, it comes out to 0.8801. And here I have the model in AB to the t form, right? So if I start in continuous growth form, it's not hard to quickly rewrite it in AB to the t form. And I can see here that the quantity is decaying about 12% per hour, right? So not exactly 0.88 here, there's that little 0.01 on the end, but about 12% per hour is the per hour decay rate. Okay, now let's answer the question, I think, right? Yes, and we answer the question by setting the output, the amount, equal to 80, right? 80 is an amount of milligrams, an output value. So that equation looks like this, right? So there's our M of t. And again, we're solving one of these exponential equations, which we've done a bunch of times. So let's just go ahead and open all of these up. Right, I first divide both sides by 80 to get this. Then to undo the exponential base e, I take a natural logarithm on both sides. When I take the natural logarithm of e to something, I just get the something, right? So that exponent kind of falls down. On the right, I get the natural log of 0.4. Then I divide both sides by minus 0.1277 to get that. Take out the calculator, and I come out with t is 7.175. So after a little more than 7 hours, the medicine will have decayed to the point where it doesn't have an effect anymore. Okay, let's do another example, this time one of exponential growth, right? So here is the exercise that I'm working on. This time I have a bacteria culture that is initially at 400 members, so 400 bacteria, I suppose. And the population in the culture grows by 3.4% per day. And I want to know, how long will it take the population to reach 1,000 members? Exponential models only go in one direction. So if you have an exponential growth model, the model just grows forever and ever. Similarly, with a decay model, the model just models continuous decay. So they're not good models for everything in the universe. Not everything just grows continuously. Some things grow and then they shrink, and then they grow and then they shrink. An exponential model is not a great choice for something like that. But there are some quantities that do behave this way, and exponential models can be useful for them. Okay, so in any event, let's go ahead and identify our input and output variables. Again, our model is going to be a function, so I'm going to clearly specify what's the input and what's the output. Here again, the input is time. That's often the case with an exponential model. Not every single time, but I would say the vast majority of the time. And again, I don't just say t equals time, I indicate how I'm measuring time, right? Time in days from the initial point, right, whenever that is for this population. And then my output, I'll call P for population. So P of T is the size of the bacteria culture after T days. Okay, so my model is going to look like this. And here, I can go ahead and write the model down right away because I'm given such precise information. I know the initial amount, 400. And I know the growth rate, right? Up above, we essentially had to solve for the growth rate. But here I'm told it grows by 3.4% per day. So I'm given the per time unit growth rate, which makes the per time unit model a good choice because I can write it down right away. Okay, so how long does it take the population to reach 1,000 members? I just set my output value to 1,000 because output is the population. So this is just kind of recapping what we just did, writing the model down there. And now I think we'll get to, yes, right? So I set my output here equal to 1,000. and solve the equation. And again, we've done a bunch of these exponential equations. So I'm going to go ahead and divide both sides by 400 to start isolating the variable, right? 1,000 divided by 400 is 2.5. Now I have a variable and an exponent, so I need to take a logarithm. It's not a base e exponential, so I'll just use a natural logarithm anyway. It won't be quite as clean as with base e, but it will still work. And the reason for this, so here I've taken ln on both sides. Let's go ahead and put some parentheses in there. And while it's this log and exponential don't undo each other because it's not a base e exponential, recall that the log of a power is the power times the log. So that t will fall down in front like this. And then I just have t being multiplied by something. So I divide both sides by the natural log of 1.034. I get this quotient, plug that into a calculator, and it comes out to about 27 and a half. So in about 27 and a half days, the population will reach 1,000 members. A word I think about changing this to continuous growth form, right? So we used per time unit growth form here, which I think makes sense in this problem. But just as an exercise, let's talk about how to convert this to continuous growth form, right? So that's what we're going to do here. What I will do is looking at this model here and comparing it to AB to the T. I'm sorry, that's way back up here. Right, I can see the value of B. The value of B is e to the k. So all I have to do is set the B value, the base, to e to the k. Well, our B value is 1.034. So I just set e to the k equal to 1.034. And that's for us a simple equation to solve now. I have an exponential base e on the left. So I just take the natural log of both sides and I get k is the natural log of 1.034. Do that on a calculator, it comes out to 0.0334. So this gives me the continuous growth rate for what that's worth, 3.34%. And I now can write the model either way, right? So this is the per time unit growth, and this is the continuous growth form of the model. And depending on what you do, one may be a little bit easier than the other, but you could use either form to answer any question about this population. Okay, so, and if we were doing this using continuous growth form, so this is just a repeat of what we did up above, right? Again, these two models are exactly the same, they just look different. So if you solve this equation, and I will not go over the steps since we've done enough of those equation solving, but it will be here in the notes, you'll note that you get basically the same thing, right? There is a little bit of a discrepancy because of round-off error. Be careful of round-off error in exponential growth problems. It tends to be more of an issue than in a lot of other problems. And here it's coming from the fact that we rounded a decimal in this case, but we're not off by very much. Okay, so just to review exponential models, the different sort of flavors of exponential models we have. If we are given, here's an example of an exponential model, right? So I just plumped down the model. What you should be able to get just by looking at the model is that this is in per time unit growth form, AB to the T form. The initial quantity is 500 and it grows by 17% per time unit, right? So just from the form of the model, we know all of that. You can verify this, by the way, excuse me. If I calculate the quantity at time unit 2, I come out with this number, 684 or so. And if I calculate the quantity at time unit 3, I come out with this number. And if I just go ahead and compute what the percent change is from time 2 to time 3, now we know what the answer should be. We're just kind of verifying that that's the case. To get percent change, remember you do new minus old divided by old, right? So that's the new minus old divided by old. If you plug all that into a calculator, sure enough, it comes out to 0.17, which is what we expected. Okay, here is a per time unit growth model, right? So what have I changed? I've changed the value of B. And what we know is that this is a decay model, right? If B is bigger than 1, the quantity is growing. If it's less than 1, the quantity is decaying. And the difference between B and 1 measures the rate. So up here, 0.17 is the rate. Down here, 0.06 is the rate, but it's decay because the B value is less than 1. So here I have a quantity with an initial value of 500 that decays by 6% per time unit. In base E form or continuous growth form, this is what a growth model looks like. Again, the initial quantity is always that number that's sitting out front, and now the continuous growth rate is that value. I know that this model is growth because there's no negative sign in the exponent because that constant is a positive. In contrast, this one is a decay model because of the negative sign in the exponent. And what we can read off of these last two models, again, is the continuous growth rate, right? So here I have a continuous growth rate of 12.5%. Here I have a continuous decay rate of 8.5%. So just looking at exponential models, we get a lot of information just from the various parameters. Again, as we noted before, we can always move back and forth from per time unit to, to continuous growth rate or vice versa. So a few words about doing that, right? Here is the generic per time unit form for an exponential model. And here's the generic continuous growth model, right? So AB to the T, AE to the KT, or RT, it doesn't really matter what letter you use for the continuous growth rate there. So if I start with something in per time unit form, and I want to write it in continuous growth form, we just use that B equals E to the K identity that we used a moment ago, right? I take E to the K and set it equal to the base, which is 1.17 in this case. It's just one step to solve that equation, take the natural log of both sides, and there's my continuous growth rate, right, 0.157. And so here we have the model in per time unit growth rate form, and here it is in continuous growth rate form. And again, these are exactly the same model, so it doesn't really matter which form you use in answering questions about the model. On the other hand, if we start with something in continuous growth rate form, right? So there's a model in continuous growth rate form. To go back to AB to the T form, I just use that sort of power to a power trick in the exponential. That is, I just rewrite this. So there's a couple ways that another way to do it is just to continue to use the identification B equals E to the K, right? So here E to the K is E to the 0.125, plug it into a calculator, there's the per time unit growth rate form. So this model grows about 13% each time unit, right? 13.32%. And again, these two models are identical, right? We just have it in two different forms for continuous growth rate and per time unit growth rate. Okay, the key questions we've been answering all along. I'm going to skip over this exercise in the video, but I will open everything up in the notes so you can look at it all later. So because exponential models only go in one direction, growth models do nothing but grow and decay models do nothing but decay, it makes sense to ask for something that's growing, how long until it doubles in size? And the thing about exponential models is because they have a constant percentage growth rate, they have a fixed doubling time. So if a model, let's say, doubles in size every 4 hours, it will double every 4 hours. So it will double after 4 hours, then it will have doubled twice after 8 hours and 3 times after 12 and so forth. In fact, it grows by any fixed percentage at regular intervals, right? So it grows by 35% at regular time intervals. But usually doubling time is sort of one of the benchmarks that we use. So suppose we have a model in continuous growth form like this. And since it's growth, that means this exponent coefficient k is positive, right? There's no negative sign in the exponent. Okay, so how would we measure, or how would we figure out rather, how long it takes this thing to double? Well, we know it has a fixed doubling time. That's what it just says. How do we solve for that? Well, I just want to figure out the initial value is a. So I just want to figure out when the quantity is 2 times A, because that's means it would have doubled. So if I set that up, indeed, just more things I've already said. If I set that up, I get this equation, right? I just want to know when is the quantity size, which is given by the output function, equal to twice the initial amount. So this looks like an equation with way too many variables, but if you divide both sides by A, the A just drops out, right? So the A's go away and I get a much simpler equation. What we're solving for here is time, right? I want doubling time. So I'm solving for t. So now I'm going to take the natural log of both sides to get rid of that exponential, right? The natural log of e to something is just the something. So I get kt on the right-hand side, natural log of 2 on the left. And finally, again, I'm solving for t. So if I divide both sides by k, I get this formula for the doubling time. I don't know that that's something that you need to remember. You can certainly if you like. You can always find doubling time by just writing down the equation and setting the model equal to twice the initial amount. And you'll always come out with this as the doubling time. Okay, so like for example, if we go back to this, that's a decay problem. Let's do the population bacteria one, right? So here we have, this is our exponential model, right? So here, how long would it take this bacteria population to grow? It is, what do we just figure out? Log of 2 divided by the value of k. So that's going to be log of 2, whoops, an extra space in there, divided by the value of k, and k is right there, right? It's the 0.0334. All right, so let me do that on my computer real quick. You can certainly do that on a calculator. So it comes out to be about 20.75. So this population will double, in this case, times measured in days, in about 3 weeks, about 21 days. Okay, that's doubling time. Excuse me, if you're dealing with a decay model, so now you're talking about a quantity that's shrinking, so it's never going to double, it's going down, not up. And now the sensible question is, how long will it take until the quantity shrinks to half its original size? This length of time is called the half-life. This is usually applied to chemicals that are undergoing some radioactive decay. So let's figure out how to determine this. Again, I start with a decay model, and I'll use continuous growth form here. Because it's a decay model, that k has to be negative, right? There needs to be a negative sign in the exponent if this is to model decay. All right, so the quantity, again, exponential models grow by a fixed percentage per unit time. So a quantity that's decaying, if it cuts itself in half in, let's say, 14 days, it's going to cut itself in half every 14 days, like clockwork. So we can figure out what this length of time is. It's called the half-life, more things we already said. All I have to do is take my quantity output and set it equal to half the original amount. So that's going to look like this, right? 1/2 times A equals AE to the KT. And as before, the A's drop out right away, right? If I divide both sides by A, I just get a half equals E to the KT. And now I'll take a natural logarithm on both sides to solve that equation, right? So I just get KT on the right, I get natural log of 1/2 on the left. And when I divide both sides by K, because I'm solving for T, I get the natural log of 1/2 divided by K. And again, you can, remember that formula is fine, or just know that to find half-life, you just take the quantity and set it equal to half the original amount and solve the equation. So in our decay example up above, the very first one where we were working with the medicine in your system, here is the model, right? So the half-life here should be equal to the natural log of 1/2 divided by the K value, and the K value is this, right, minus 0.1277. All right, so again, I'll do this on my computer. And I get 5.8, we'll call it, round it off there. Okay, so that means that this medicine cuts itself in half every about 5.5 hours, right? 5.428 hours. Okay, let's move on. Again, these exercises I will open up in the notes. They are from the notes and exercises. But let's talk about a couple of more examples: Newton's law of cooling and the moment magnitude scale. And I think that'll probably be good for this video. So Newton's law of cooling is just kind of a special case of exponential model. Again, not introducing any new mathematics here. And the situation it models is when you have an object that differs in temperature from its environment. So for example, you take an ice cube and drop it into a large pot of warm water is an example. Or if you take a hot ingot of metal and plunge it into a cold bath, you have an object that is at a different temperature than its surroundings. And the way we will model that is we will model the temperature of the object as changing to meet the temperature of the surroundings. So this is an approximation of reality. It's not quite reality. And in fact, when you put an ice cube into a large vat of water, the temperature of the ice cube goes up, but the temperature of the water also goes down a little bit. But we're just going to assume that the object is the thing that changes in temperature. So here's an example. Right, I take something out of the oven at 165 degrees Fahrenheit, and I put it in the refrigerator, which is 35 degrees. After 10 minutes, the cheesecake has cooled to 150 degrees, and we want to know how long do we have to wait until it's down to 70 degrees. Okay, so the key to Newton's law of cooling is what we build a model for is the difference in temperature between the object and the surroundings, not the temperature of the object, the difference in temperature between the object and the surroundings. So I'll let U of T be the difference in those two temperatures, and I'll measure time in minutes after I put the cake in the fridge. Time's being measured in minutes here, so that seems to be a sensible unit. And we will assume that U follows an exponential model, right? So this is Newton's law of cooling. And I know that this difference is going to decay because I expect the temperature of the object to change to meet its surroundings, right? The hot cheesecake is going to cool off in the fridge, so that difference shrinks over time. That means I have a model that looks like this, right? I have a minus K in the exponent of the growth model. Okay, again, the key in going through this is remembering that U is the temperature difference, not the temperature of the object. The initial difference then is not 165, but the difference between the object and its surroundings. So the fridge is at 35, so 165 minus 35 is 130. So I can partially specify my model, right? The A value should be 130. Now I'm going to use the other piece of information here that after 10 minutes it has cooled to 150 degrees to figure out what the K value should be. Oops. After 10 minutes, the cheesecake has cooled to 150 degrees. This is not a temperature difference, however, it's just the temperature of the cheesecake. The temperature difference at that point, right, at T equals 10, is 150 minus the fridge temperature. And again, our modeling assumption is that the fridge temperature doesn't change, right? The cheesecake cools to meet the temperature of its surroundings, but not vice versa. So after 10 minutes, the difference between the object and its surroundings is now down to 115, right? Less than it was before. That's the U value. All right, so that means that this is an exact repeat of what I just said. So I don't think we need both of these cells here. right? So u of 10 is 115, right? The difference at time 10 is 115. So I'll just take my, here's my model for the temperature difference. I'll plug in a t equals 10, and that looks like this, and set it equal to 115. And I get one of these exponential equations that we've solved a bunch of times now, right? So I'll divide both sides by 130. And that looks like that. Take the natural log on both sides. And that looks like that. And divide by -10. And you'll notice here that I've saved all the computing for the end, right? That is, I did not do this on my calculator or this on my calculator, but waited until the very end and did the calculating all at once. That's because I'm trying to keep round off error down, and round off error can be a problem in exponential models. All right, so I have my k value, which means I have the fully specified model, right? U of t equals, it was this, 130 e to the minus kt, but now I have k, so there's the full model. All right, so now I'm ready to answer any questions I need to answer. What do I want to know? How long until the cheesecake has cooled to 70 degrees? Now, I'm not going to set u of t equal to 70 because u of t is not the temperature of the cheesecake. It's the difference in temperature between the cheesecake and its surroundings. So when the cheesecake is 70, the difference will be 35, right? 70 minus 35. And that's what I'm going to wind up setting u equal to. So I think there's going to be some repetition. Yes, right? So when will the temperature difference be 70 minus 35 equals 35? So I set u of t equal to 35. That's exactly the same thing, so we don't need that. And here's the equation that results, right? So the left-hand side is u of t, the right-hand side is 35. And again, hopefully by now, you are very good at solving equations like this. Here's what the solution looks like. Right, divide by 130, take natural logarithms, divide by minus 0.0123, save all the calculating for the end, and I come out with this number, about 107 or so. T's in minutes. So it will take a little less than 2 hours for the cheesecake to cool down to 70 degrees according to this model. Okay, again, no new math here. It's all just an exponential model, but it takes a little bit of practice to get good at modeling the temperature difference using an exponential model. Okay, one more example, this time of a logarithmic scale, something I think we mentioned in the previous video. The moment magnitude scale is a scale for measuring earthquake intensity. And we don't have to know a ton about earthquakes, just that you can somehow measure the seismic moment of an earthquake. That measures how strong the earthquake is. And if you plug it into this formula, you get a measurement on this moment magnitude scale. Now, the thing is, these seismic moments tend to be enormous, so it's hard to make sense of what they mean. And this moment magnitude scale puts them on a scale that's a little easier to understand. So let's try the following exercise. I'm going to compare two earthquakes, one that has a 5 value on the scale and one that has a 7 value on the scale. So the 7 earthquake is stronger, but how much stronger is sort of the question that we're asking. Well, the first thing I'm going to do is I'm going to take this first earthquake value 5. So that's an m value, right? So it goes on the left side of this equation. And so I'll just set 5 equal to the formula. And in the numerator, what I want is the seismic moment of the first earthquake, which I will call S1 for first earthquake. Well, there's only one variable in this equation, the thing that's highlighted in blue, so I can solve for it, right? So I'll multiply both sides by 3/2, right? That's how I get rid of the 2/3, right? I multiply both sides by its reciprocal, 3/2, and 3/2 times 5 is 7.5. Okay, so now I want to solve for S1. I have to get rid of that logarithm. That's a common log, right? There's no subscript, so it's log base 10. So I'll raise 10 to both sides. Right, and when I raise 10 to both sides, 10 to the log are inverses, so I just get the S1 over 10 to the 16th, and I get 10 to whatever was on the left. I think we may have had a little hiccup in the recording here. So I'm just going to go back to the beginning of this point. I think I recorded fine up until then, right? So I have a scale value of 5. That's an M value. So I set it equal to that right-hand side, right? S1 is the seismic moment of the first earthquake. Multiply both sides by 3/2, raise 10 to both sides. And the next step I'm going to take is to multiply both sides by 10 to the 16th power. Right, that'll get rid of that 10 to the 16th in the denominator. So I get S1 is equal to 10 to the 7.5 times 10 to the 16. You can see some of the enormous numbers that show up here. And that's 10 to the 23.5, right? So that's the seismic moment of the first earthquake. That's a very big number, right? So that's like a 1 with more than 23 digits after it. Okay, I'll do the same thing for the second earthquake. So now my scale value is 7, right? So the left-hand side is 7, but the solution to the equation is going to go very similarly to up above, right? I multiply both sides by 3/2. 3/2 times 7 is 10.5. I raise 10 to both sides, multiply by 10 to the 16th. Remember, I should have mentioned when you multiply powers of the same base, you add the exponents, right? So up here where I'm highlighting now, 16 plus 7.5 is 23.5. That's where that exponent comes from. Down here, I have a 10.5 exponent and a 16 exponent. And when I add those, I get 26.5. The easiest way to compare S2 to S1 here is to take the quotient. Right, so if I divide S2 by S1, I get this ratio of powers of 10. And when you take a quotient of powers of the same base, you subtract the exponents. 26.5 minus 23.5 is 3. So, and 10 to the third is 1,000. And what this tells me is that S2 is 1,000 times S1. So one of the advantages of a logarithmic scale is it allows us to take quantities that are very different, right? So I have two quantities where one is 1,000 times the other and put them on a scale where their values are not too far apart. Okay, that's good for exponential models. Take good care of yourselves, folks.